Assalamualaikum and hi everyone. Today our group will be presenting on a critical topic within modern physics and sustainable energy, waste management in fusion and fission system. To begin, let us look at the core of the issues. When we talk about nuclear energy, we are looking at two entirely opposite physical processes that create completely different type of waste. Nuclear fission works by splitting heavy atomic nuclei like uranium-235, which leave behind highly unstable, high-level radioactive fragments that require thousands of years of isolation. On the other hand, nuclear fusion fuse light isotopes like deuterium and tritium together. This creates completely safe, non-toxic helium gas as a primary byproduct, though it causes radioactive activation inside the reactor cell's walls. While both options provide incredible zero-carbon power, handling their unique waste stream safely is the ultimate puzzle we must solve. This investigation is deeply relevant to Chapter 9 of our syllabus. It allows us to take theoretical classroom concepts such as radioactive decay equation, ionizing radiation modes, and isotope half-life and directly apply them to a real-world industry infrastructure. Solving this waste puzzle carries massive urgency today. It is the single biggest hurdle to gaining public trust for the global clean energy transition. Furthermore, this topic actively pushes the boundaries of modern physics by forcing scientists to engineer advanced new materials that can withstand intense, high-energy radiation field without breaking down.
Now, let's talk about research challenge and the solution. First challenge, which is nuclear fusion, is the structural material activation 14 MeV neutrons. What is the problem? The problem is the high-energy neutron produced by deuterium-tritium DT fusion smashed into the reactor walls, transmuting stable elements into radioactive isotopes. This turns the physical reactor structure into thousands of tons of radioactive waste upon decommissioning. So, the solution is low activation materials lamps. Researchers are developing advanced steels like Eurofer and vanadium alloys. By replacing common structural elements like cobalt, nickel, and molybdenum with low activation alternatives like tungsten, tantalum, and manganese, the radioactive waste decays rapidly, returning to safe clearance levels in just 100 years rather than millennial. Next, nuclear fission. The challenge is corrosion and leachability of waste forms. The problem is high-level waste HLW generates intense decay, heat, and radiation. Over hundreds of years, if groundwater ever reached the waste, traditional storage materials could corrode, causing radioactive isotopes to leach into the water table. So, the solution is advanced vitrification and ceramic material host phase. Liquid HLW is mixed with crushed glass, freezed and heated to over 1000 Celsius to form a highly stable borosilicate glass, which is vitrification, or synthetic rock, zinc rock. These crystalline ceramic and glass matrices trap radioactive elements on a molecular level, preventing them from dissolving in water even under extreme underground pressure and temperature. Next, the physics of fission waste. First, fission waste characteristic. It can be done in many ways, such as first, spent fuel, composed of uranium, plutonium, and highly unstable fission fragments that remain intensely radioactive. Next, long half-life. Isotopes like Pu-239 have a half-life of over 24,000 years, necessitating a geological mindset for disposal. Next, high-level waste status, which is HLW, accounts for 95% of radioactivity, only 3% of total nuclear waste volume. Next, radioactive decay modes. First, we have alpha decay. It is an emission of helium nuclei, has high ionizing power but low penetration. Next is beta decay. It is an emission of electrons. It moderates penetration that requires aluminium shielding. Lastly, gamma decay. It has high energy electromagnetic radiation, and it is extremely high penetration that requires lead or thick
Thank
concrete.
you, Mamoto. Hello, my name is NURIN and I will be covering the physics of fission waste. Unlike fission, fusion does not produce high-level chemical waste or spent fuel rods. The actual product of fusion reaction is simple, non-radioactive helium gas. However, a process known as neutron activation takes place. During the reaction, high-energy neutrons moving at 40.1 MeV constantly bombard the structural containment walls of the reactor. This intense neutron flux converts the stable atoms inside the steel walls into radioactive isotopes, creating intermediate to low level waste that eventually must be decommissioned. To visualize this clearly, let's look at this slide. Fission waste comes from the fuel itself, lasts for over 100,000 years, and demands deep geological repositories. Fission waste, conversely, comes entirely from the activated structural material of the reactor, because these materials have much shorter radioactive lifespans and about decaying safety from 50 to 100 years. They can simply be stored on the surface or recycled within a single human lifespan. Additionally, fission carries absolute zero risk of a runaway meltdown, making it fundamentally safer. You might wonder how this applies to our daily lives. The exact physics behind radioactive containment and shielding engineered for nuclear waste directly influences how modern hospitals safely handle, store, and discard medical radioactive isotopes. For example, cobalt-60, which is used daily in life-saving cancer radiotherapies, relies on these identical shielding principles. Furthermore, these rigid geological isolation designs ensure that our local water tables and communities are completely protected from ambient ionizing radiation.
Next, high-level fission waste has sparked major controversies globally. There is intense public and political pushback regarding where to build permanent underground, deep geological repositories as seen in a project like the Finland's Onkelo repository. To counter this long-term waste issue, a brilliant advancement in modern physics is the development of LAFM steels. There are specially engineered alloys designed for a fusion reactor that do not trap radioactive isotope easily. This drastically shorten the waste half-life, allowing reactor part to be safely recycled and or reused within just a few decades. Next, looking forward to our own professional self-development. This topic opens up several exciting career paths within modern physics. First is a nuclear waste management consultant who design radiation shielding and manage decommissioning logistics. Second is radiation health physicist, a career center on setting industrial safety limit and protecting workers from exposure. Lastly, one could become a nuclear materials research scientist focusing on synthesizing new alloy that can withstand heavy neutron bombardment without activating. So now we will talk about specific skill mapping and execution. To immerse ourselves in professional career in nuclear waste management, it is required to actively acquire in specialized technical and analytical skill, which also called technical software mastery. This skill is about learning and practicing Monte Carlo and particle (MCNP) simulation code that used globally for analyzing radiation shielding and transport. It is used by nuclear physicists to stimulate how neutrons, electrons, and gamma rays interact with different shielding materials. Beyond software, a deep domain expertise in radioecology is essential. This involves studying how the radioactive isotopes interact with the environment, ensuring that if low-level waste is buried, it will never contaminate local ecosystem or food chain. Finally, we must balance this heavy technical skill with professional risk communication. A nuclear physicist must be able to translate complex stochastic radiation equation into clear, transparent safety metrics that public policy makers and communities can easily trust. Next, we're going to talk about goal setting and continuous self-development. As we all know, the nuclear industry changes very quickly, not just because of science, but also because of safety rules, laws, and politics. So, adaptation to the evolving nuclear regulation is a must skill in nuclear fusion and fission sector. Then, as a short-term goal to develop these skills, attending open access to technical webinars hosted by the International Atomic Energy Agency and pursuing baseline radiation safety officer certification will make your resume stand out. Lastly, as the long-term strategy, Malaysia doesn't currently use nuclear power plants, causing local infrastructural limitations. So we need to build professional network within the World Nuclear Association and targeting international postgraduate opportunities in active nuclear energy nations. Lastly, in conclusion, the comparison between these two nuclear system waste is clear. Nuclear fission leaves behind a high-level radioactive waste that requires complicated, deep underground storage for thousands of years, while the fusion provides a much cleaner alternative. It doesn't create high-level chemical waste. So, conquering the physics of nuclear waste management is the absolute final barrier that we must cross. By solving this problem, we can finally unlock a future of safe, limitless, and completely zero carbon energy for the global population. This topic also shows us that a great career isn't just about formulas on a whiteboard. To be successful, we must commit to continue learning, stay up to date with changing global safety regulation, and adapt to international opportunities.